weight shift control 3-2 components and systems. Let's delve into the intricate systems that govern the behavior of weight shift control aircraft wings. In particular, we'll explore reflex systems, pitch control systems, roll control systems, and trim systems. As we've discussed in our exploration of aerodynamics, maintaining positive pitch stability is crucial, especially during low or negative angles of attack. To address this, various reflex systems come into play in emergency situations. Reflex systems are commonly employed in wings to prevent dropping at unusual angles of attack. Additionally, they contribute to increased reflex at higher speeds by creating drag that pulls up the trailing edge. For wings utilizing struts without a king post, a specific system is introduced to ensure the inboard trailing edge remains elevated. Moving on to pitch control, the system revolves around a straightforward hinge on the keel at the hang point. This hinge allows the pilot to control the pitch. The hang point wing attachment ensures the control bar remains perpendicular to the longitudinal axis of the aircraft, enabling the raising and lowering of the nose. Roll control, governed by the movement of the control bar from side to side, influences the rotation of the wing around the wing keel. The control bar's side-to-side motion causes the carriage to roll around the wing keel relative to the carriage itself. While shifting weight alone could induce banking, practical flight demands more. As weight is shifted, the keel is drawn closer to that side's leading edge, limited to a movement of 1 to 2 inches each side of center. This limited keel movement is sufficient to warp the wing, altering the twist side to side and, consequently, rolling the aircraft. The overall roll control is meticulously adjusted by designers, considering factors such as sail material, leading edge stiffness, wing twist, keel travel, airfoil shape, and wing planform. Lastly, trim systems play a crucial role in relieving control pressures and enabling pilots to fly at different hands-off trim speeds. Ground-adjustable trim systems, a common method, involve adjusting the wing attachment hang point to set the tone for the aircraft's trim speed during flight. Another method involves increasing tension on the crossbar in flight, adjusting the trim speed and altering the wing's characteristics. This, however, comes with trade-offs, impacting the wing's roll control and stiffness. Intricacies of ground-adjustable trim systems are documented in the pilot's operating handbook, providing essential insights into pitch settings under different loads. It's essential to understand the nuanced adjustments required for optimal performance. Delving into the intricate realm of in-flight adjustable trim systems, we find that their dynamic capabilities confer several advantages, as we'll explore in later sections dedicated to flight. Various manufacturers offer diverse in-flight adjustable systems, and a prevalent method involves manipulating the trailing edge. In this common approach, a crank on a downtube serves as the interface, controlling a wire that extends to the wing's zenith. By adjusting this crank, pilots can raise or lower the trailing edge, consequently altering airfoil reflex and affecting the wing's speed. Notably, hydraulic or electrical systems can also come into play, facilitating the adjustment of the wing's hang point for different in-flight trim systems. An alternative pilot-actuated trim system during flight involves an elastic mechanism. Here, the pilot increases tension on the elastic system, leading to a raised nose, which proves advantageous during climb and slower flight. Shifting our focus to the carriage, a distinct entity divorced from the wing, it stands as a self-sufficient structure capable of autonomous movement without the wing. The carriage constitutes a significant portion of both weight and cost in the weight shift control aircraft. Carriage designs span a broad spectrum, ranging from rudimentary open trikes to sophisticated models that seamlessly integrate cowlings. The more intricate trikes, boasting numerous adjustments for both pilot and passenger, aim to enhance comfort and reduce fatigue during flight. However, it is crucial to note that heightened complexity in trike design correlates with increased costs, weight, and power requirements, especially when compared to similar wings. Structurally akin to the wing, the carriage employs a design founded on a multitude of structural triangles. While specific details may vary among manufacturers and models, the carriage typically encompasses a mast, keel, and front tube as the primary triangle components. At the zenith of the mast, the wing finds its attachment point. A seat frame, affixed to the mast and keel, imparts rigidity to the primary components while serving as a foundational structure for the pilot and passenger. Landing struts affixed to the rear wheels contribute to the main landing gear structure, whereas the front wheel's landing gear structure is facilitated by a front fork. An engine mount, securing itself to the mast, provides the necessary structure for the propulsion system's attachment to the carriage. The landing gear of a weight-shift control aircraft plays a pivotal role, providing crucial support on the ground and effectively absorbing shock to mitigate stresses during landings. Let's delve into the intricate details of this fundamental component. The landing gear comprises the front wheel, which bears a lighter load and is primarily employed for steering, and the main or rear landing gear, tasked with shouldering the majority of the aircraft's weight. The front steering fork, associated with the nose wheel, is equipped with footrests utilized by the pilot for ground steering. In terms of controls, the foot setup mirrors that of driving a car, with the left foot pedal serving as brakes exclusively for ground use, while the right foot manages throttle and power both on the ground and during flight. Notably, the front fork generally possesses camber, allowing it to naturally track in the direction of travel, akin to a motorcycle front fork. In training scenarios, a second steering control is integrated, featuring a connecting rod that allows the instructor situated in the rear to steer the carriage on the ground using the nose wheel. Steering dampers may be employed to stabilize the front wheel, preventing shimmying at higher speeds during takeoff and landing. Shock absorbers, or the tire itself, contribute to mitigating shock. The front wheel commonly employs a disc or drum brake, with options for mechanical or hydraulic actuation. While a front brake is lighter and simpler, some carriage brake systems leverage rear brakes. The inclusion of a parking brake proves invaluable for securing the aircraft on the ground without necessitating additional chocks. Diverse parking brake systems are employed by different manufacturers to achieve this. Turning our attention to the main landing gear, comprised of the two rear wheels, we observe a concentration of weight owing to the center of gravity being much closer to these wheels. This weight distribution on the rear wheels is particularly significant during taxiing, takeoff, and landings. Numerous other main landing gear configurations and shock-absorbing systems are prevalent, including wire bracing with bungee cord shocks, fiberglass or flexible main gears devoid of struts, and various hybrid variations. Carriages designed for higher speeds may incorporate streamlined landing gear systems. As discussed in the earlier section on the nose wheel, the carriage may feature main landing gear brakes on both wheels, employing drum or disc brakes controlled by mechanical or hydraulic mechanisms, with diverse designs and options across manufacturers. The role of tires extends beyond mere contact with the ground, as they also contribute to shock absorption during landings. Large tundra tires, for instance, provide significant shock-absorbing capability and find application in operations on soft fields, rough terrains, and sandy surfaces. Conversely, faster WSC aircraft utilized for airport operations often feature narrower tires to minimize drag. Extending the scope to landing gear designed for water and snow operations, we encounter specialized systems tailored for weight shift control C, WSCS, and ski-equipped scenarios. In the case of ski-equipped configurations, skis may replace or supplement the wheels. For WSCS, two primary systems, flying boat and pontoon, facilitate operations on water. The flying boat involves fitting the WSC aircraft into a solid or inflatable boat, securing the fuselage in place. Suited for rougher seas, this configuration typically necessitates a larger wing, resulting in a slower flying WSC aircraft. The boat's stability in rough seas also aids in minimizing water splashing, ensuring a drier experience for the pilot and passenger.